Okay, we are live, and let's hope some people join us. Okay. Right here. Please say hi when you are there. It's pretty windy out.
Yeah.
Okay, while they're hopefully logging in soon, here's a lab back to you
Oh, okay.
and everybody else, but there you go here. Looks good. Hey, I got one. Shilpa. Yeah. Good. Okay. I'm going to try and move that back as far as I can. Oh, look at that. Look at that. Nice. Okay, so we can get, hopefully, more that can be seen. All righty, so let's go ahead and begin. We're going to go here until 11:15, and if Aaron, that's okay, we're just going to go straight through, and then 11:15 we'll just stop, and you have then time off after that. Okay, because that way it's a little easier just to do one live stream with everybody. And well, that's a student book. Let's get mine. So two things today. We're gonna take a look at salts and how to figure out if they're acidic or basic and what to do. And then we will, well, actually before that, we're gonna take your questions. So you're working, I think, on chapter 4 stuff. So let me know if you've got some things to ask about. Aaron?
Not yet.
No? Okay. All right. So chapter 4, Shilpa, I know you're catching up, so that's all right. Anybody else out there? I see 3 people. If you're out there, say hello so I know who is there.
I'm getting some notifications that apparently, like Quinn said, it said that the video was unavailable.
No, it should be available because Shilpa's on there, and I sent the link through the, yeah, so tell them I sent the link through the Google Classroom. And it should be able to click on there. It's open. It's available for the public. I made it public today.
Oh, there's also Sarah and Rhea can't comment.
Ah, they can't comment for some reason. I don't know why that would be because I have the comments on. So everybody.
Sometimes you need to change like to Google Chrome or something.
Yeah, they have to change to that, you mean?
Yeah, I think that.
Okay, so Aaron says if people need to change to Google Chrome or something, you may have to do that to be able to comment. But for now, if Aaron will allow this, folks, if you have any questions on chapter 4, could you send them to Aaron over our group WhatsApp? I assume that's what you're looking at, Aaron, or whatever WhatsApp you guys are using. So if you have questions, why don't you mail them in now? And then we can do them together on the board. So maybe you can try another platform or whatever so you can comment. But if not, you'll have to ask either Shilpa or Aaron to put up problems that you'd like to see from chapter 4. I will turn to chapter 4. Maybe I'll do one to kind of warm everybody up. That might be a good way to start. Chapter 4 is about solubility. So you know what? Let's warm up by doing a, Quinn, I still have your book. So alas, it's all graded and it's here for you, but I don't have you. So you'll have to get it tomorrow. Or today if you want to stop by and get it from the secretary or something. Okay, very good. All right, then let's do a little review. Okay, so how about this? If Let's try and make it an interesting one today. Yeah, that's what I want to do. If 0.0010 molar magnesium nitrate, let's make it 200 milliliters, is added to 200 milliliters of 0.00, oh, what the heck, 10 molar NaOH, will a precipitate occur? Okay, so where I'm looking at is page 255, but even without that, Chopin Quinn and anybody else and Aaron here should be able to tell me who will not be in that precipitate, and therefore what precipitate might I actually be getting. So the chemicals are magnesium nitrate and sodium hydroxide. So what's my possible precipitate, I guess, is what I'm trying to say. Or what could I throw out? Mentally throw out the ions we said are usually spectators and tell me what precipitate it could be. Let's see if Chopin and Quinn can punch it in there. Aaron, you probably know. Yes, Aaron knows. So can you guess what that will be? And then we can play our little game show game with the folks, the studio audience and the audience at home. Nitrate could be thrown out. Yes, good, it's gone. Something else too. And Quinn has it. So the possible precipitate, because sodium could also be thrown out, is, thank you, Quinn, magnesium hydroxide. So let's do it like this. MgOH2. Even though it can make a precipitate, in this sort of problem, it's actually easier to think of it as doing this. In other words, I've got Mg2 plus, well, I should ask Aaron, you're here, plus, what would the rest of it be, Aaron?
2OH.
Thank you very much. Okay, so then they can write the KSP expression, but I'm not going to call it KSP. I'm going to call it KSP's younger sister called, Quinn should know this, Q. Okay, so the Q expression will be in parentheses. Aaron, why don't you go ahead?
Mg and then times plus times the concentration of OH minus squared.
Super. Okay, so now we got to go back to the problem. Remember how it, thank you, Quinn. I knew you knew it. So let's go back to the problem and actually play that little game. And I made the game nice today. Sometimes they do this on a multiple choice question. So check out this. I got 200 milliliters of this one added to 200 milliliters of this one. What does that mean? What happened to the concentrations of both chemicals? I could actually just kind of say that in my Q expression. Or I can write it over here to the greater. Both concentrations will have them. Thank you. Thank you, Brent. Will be halved since volume is double or 2 times. Sometimes I think of writing a note to the grader if it's an FRQ just to let them know quickly what I'm doing. And then I just do this.
Do I still have a question?
Yeah.
She asked, how did we know to use Q?
Oh, okay. Remember, this is, what did Sherry call it? Okay, Sherry doesn't call it Q. She calls it tip. So my apologies. Tip. So, and what the heck did tip stand for? trial ion product. She's the only one in the world that I know that uses that, but it's kind of a nice idea. So trial ion product, that's the same as Q. Remember the deal? We got to see if the trial ion of the tip, thank you, Gwen. We got to see if the tip is greater or not greater than the KSP value, which we'll look up in a second. So we got to find the tip, which is really just some kind of Q. Okay, so because we set this to the grader, we can just put in the numbers that we know are going to be. So instead of 0.001, because we're doubling the volume, the new concentration will be at 0.0005. And I can put another O to keep sig figs. And for the OH minus, I think it's the same, isn't it?
Yeah.
So 0.00050. But I got to think about this for a minute. Yeah, it's 1-to-1. It's 1-to-1. Okay, so that is correct. So we've cut each concentration in half. This one's going to be squared, of course. And let's go ahead and get everybody a tip, I guess we'll call it, and see what that number is. And then we'll look up the KSP and see if we have a precipitate or not. So, Aaron, I'll let you punch that thing out. Folks at home can pull out a calculator and type away, please. Oh, the excitement is building here in AP Chemistry. I'll continue on the other board because it's so messy.
I got 1.25 times 10 to the negative 10.
Let's see if others got the same. Does that check with somebody else out there? Give me a thumbs up or give me a yes or whatever in the comments. That would be swell.
Ria's saying that comments don't work on Google Chrome either, so I think there's...
That is so strange because I got comments from, hey, Noah Diaz there. Hi, super. Okay, so Noah, we're doing a little warm-up problem, seeing if we got a precipitate or not. So there's our tip, and I think that's right. It looks pretty good. Let's see if anybody else gets it, but that looks good, Aaron. And now let's look at the KSP and see what it is. Magnesium hydroxide, ready? The KSP is 5.6 times 10 negative 12. And so, is our tip bigger? Do we get a precipitate? Answer starts with a Y. How exciting. Yes, we got a precipitate. And what a way to start our day in AP Chemistry. Okay, so that should be review for you. And you might say, Mr. Weiss, you picked such easy numbers. Do they ever do that? Just have like even volumes? Yes, they do. Sometimes they do this 200 and 200 or whatever, so you can just cut the concentrations in half. So look for that trick. Okay, Aaron, anything you want to ask about with this?
No.
Okay, all right. So once again, I'll just say, if you have any questions and you can comment, put them in the comment from chapter 4. Otherwise, just text Erin, and she's here, and she can tell me if there's some you'd like to have us look at as you're working on chapter 4. Yeah. Okay. So hopefully that's all right. I'll wait just a minute to see if you type anything or contact Erin with any questions on chapter 4. And if not, we'll continue on. So while you think, I'll get ready for our next action. Oh, the room changes. That's where I wonder. I wonder where those were. Okay, I see nothing so far. Aaron, you see nothing so far? Then we're just going to start with our goal for today. So our goal today is to have you guys be able to predict if a salt is given to you and you stick it in water and stir it, if the solution is going to be acidic or basic. Okay, just for grins, I want to do one with you. So stand by. I'm going to get an actual chemical. In the meantime, I want all of you who've been here a while and used this before to tell me, we're going to talk soon about indicators. Universal indicator colors. I want you to tell me what that is in acid, neutral, and base. And I'll put those in just a sec. Let me go back and grab a chemical and some universal indicator. It's water. Oh, good gosh, can't be easy, can it? Okay, so
Sarah answered. She said that bases are like blue and purple.
super. Correctamundo. Good, Sarah. So here we go. Bases are bluish, so I'll put some blue chalk over there.
And Rita's saying acids are orange and red. And then
You got it.
green in the middle.
Thank you, Rhea. And in the middle is sort of yellowish.
Oh, good. I always thought it was green.
Well, yellow, green. It kind of depends on the one you make up. I'll tell you what, we'll do a little both, Aaron. How's that? Yellow, green. Okay. Good. Okay. There it is. There's one of the little test plates I have. Here they got yellow absolutely in the middle, but depends on the batch you make up and the certain variety you get. Universal indicator is a mix of indicators, so it's several chemicals put together. That probably accounts for some of the variance. Yeah, and Shopa had the one, it's red in acids. Good. Okay, so well, we're going to kind of use that to play our little game here. And here's my game. Actually, I want to do one with you. Let's do one with you. Let's do this. Okay, I'm going to leave that up there because we need those colors in a little bit. And again, most of you have had that before, but if not. And by the way, thanks everybody for joining us. Okay, so here we go. So here's really our question of the day. If salt is added to H2O, will solution be acidic, basic, neutral? Okay, let's take an example. All right, NaCl. What a boring example. You can kind of guess this one, okay? Na comes from, and I'll ask Aaron here, what strong base does that come from?
NaOH.
You got it. Comes from the strong base, NaOH. So what that means is Na plus will not affect your pH. So we don't care about it. It's not going to do anything. However, Cl minus comes from what important chemical?
HCl.
HCl, so strong acid. So that won't do anything. So it should end up being what sort of solution? Salt water or table salt water.
Neutral.
Yeah, thank you. It should be neutral. So I know that was boring. Let's give you one that's more interesting, okay? Okay, what if I give you this? What about PbNO3 2? So let's put that in water, okay? Who does nothing out of there? So what ion does nothing? I know Aaron knows here. So folks at home, maybe you can type in, what ion can I throw out that will not really affect the pH? Thank you. Good. Got lots of responses. Quinn, Noah, say the nitrate. So therefore, we're going to cross it out, and we're going to throw in the Pb2 plus. We're going to throw it in some water and let it swim around. Thank you. Everybody knew that. Appreciate it. And so think of water being what? OH minus and H plus. The water's, or the Pb2 plus, Aaron is going to grab what from water? OH minus. So we can have it grab 2 if you want. It doesn't really matter. So I better make 2 waters. So theoretically, I get PbOH2 forming. And then what's left from the poor waters that I ripped apart? And I'm sure Aaron knows, maybe you can type in. What is left that's rather important left from the poor waters? All right, Aaron, you can draw it in the air. Pretty good, huh? Good job. Thank you. Thank you. You got it, Shipa. All right, so H, and it's going to be H plus, and let's just say there's 2 of them. So probably look that way. It won't necessarily be a H2 gas, but H2. That's going to make the solution. So the solution is, therefore, what? Acidic, basic, or neutral? Hint, it ain't neutral. And you guys are so good. I know you know this anyway, because you all knew the H plus thing going. So acidic, basic, or neutral? That is the Shakespearean question. And acidic says no D. Good. And of course, from earlier, I should get a red or orange color if I put an universal indicator into that solution, right? With salt water, it'll be just some yellowish green, okay? Okay, so now it's your turn. Ready? Here's the chemical. I'll tell you what it is in a moment. And you're going to figure out on paper what's going on and tell me the color to expect from my universal indicator when I actually do it here. We're doing a demo. Absolutely. So, I don't want to erase that. So I'll erase this instead. Okie dokie. So here's your demo. Demo of the day. The demo is your challenge, and then we'll do it with you live. It's in German, but I'll give you the English phrase. So if sodium sulfite is dissolved in water, universal indicator added will make solution. All right. And there you're going to put in a color, and you can also put in acidic or basic. And yeah, that's all you need. So hopefully you have the ions memorized. So figure out what one's doing something, throw it in water. You want to have an equation to prove it in case you had to prove it to a grader. And then figure out what's going to happen. And while you're doing that, I'm going to get the stuff. Here it is, natrium sulfite. Okay, there it is. And we're going to take some out. And it's, not surprisingly, a white crystal. So there it is. Looks a lot like table salt, but you wouldn't want to eat it. We don't need much, that's plenty. A question from Noah Delph. Sorry, no, I didn't see that. Are the OH minuses neutralized and therefore not counted? It's not that they're neutralized, it's that they're bound up back with the lead. So they're out of the picture. So the OH minuses are like pulled out, and if they grab onto the lead, you just got to look at who's left behind. So it's not that they have no effect. They're not OH minuses. They're part of PbOH2. Noah, is what's happening. Okay, there's my stuff. So here you go. I'll turn the camera down a bit. And then we could just add some water, distilled water. I could spray it, but I'm too lazy, so I'm just going to pour some in. Here's a side question for you to think about. Should this stuff be soluble? Sodium sulfite. And your answer better be yes, because it's dissolving quickly. It's almost see-through already, just like NaCl. Sodium is very soluble, so You're welcome, Noah. So sodium's very soluble, and there you go. It's already dissolved in water. Okay? Okay, so I want from everybody, you can mail your answer to Aaron, and folks who have comments can type it in. Tell me what color I'm going to get when I add the universal indicator. So I want you to do a little prediction for me. Will I get yellow? Will I get red? Will I get blue? Please type in your answers now. And Aaron can point to one on this stick. What do you think, Andy? You got a guess? Uh-huh.
Somewhere around here.
Uh-huh. Cool. Okay, I'll put that up just a minute so I can see a little bit. All right, type it in. What's your guesses? I want a color. Come on. So Noah, Quinn, Shilpa, give me some color. I got a color from Quinn. And I also got a color from Aaron here in the classroom already. How about Shilpa or Noah? Bluish, okay. So I got a color from Noah.
And Sarah says blue or purple.
Blue from Sarah. Okay, let's see what we got. Here we go. I would ask Aaron to do a drum roll, but it's so windy out, probably you're not going to hear it out there in cyberspace anyway. Okay, let's try and do this here where you can see it. We need white, don't we? I know. The suspense is killing everybody. I know it. Here we go. Okay, you ready? So I got it white here, and I'm going to I'll put in a couple drops. What the hey? Oh, man, beautiful. The lovely color of the sea. Look at that, beautiful dark blue. So it's basic, baby. Wow. Look at that sucker. So good prediction, everybody. And hopefully,
Leo says beautiful.
oh, thank you. I thought so too. Yeah.
Wait, isn't that the color that makes the solution?
That's the color.
Right.
And makes the solution basic and blue. B&B. It is a lovely color. Just gorgeous. So look at it against the white. Look at it. It's just beautiful color. Okay, so then just to back it up, if I had to do that, sulfite is SO3 and 2 minus. All right. And so if I add some waters to that sucker, and I'll need a couple of them, and I'll just ask Aaron, what'd you put for your reaction there, Aaron?
H2SO3 and 2O minus.
Beautiful. Thank you, Aaron. So the OH minuses definitely are the reason we got that basic blue color. Well done, my people. Let's do some more. So I'm going to do a whole table with you and see if we can do them fairly quickly. You can even do some of these kind of mentally. And yeah, so let me think how much room I need and how much room you need on the board. So let's do this. Let's do chemical. List any spectators. And then we're going to say acidic, basic, neutral, and then we're going to say proof. And the proof will be a chemical reaction. So let me see it. Everybody can see that at home. So make yourself a little table. Let's do 4 chemicals. So if you got room, I'll try and make it a nicer table than I usually do. So our 4 chemicals will be NH4, do I want to do that one? Yeah, I. And then we're going to do ZnNO3, 2. We're going to do KClO4. And we're going to do Na3PO4. So I'll try and make that nice while you guys are thinking. So there you go. That'll probably take a little longer, our proof over at the right there. Okay, so work on those at home. Exactly, Shilpa, greenish blue. Exactly, sodium was a spectator in this case. Right on, Shilpa. So do some more. I'll take a little walk around the classroom while you do so.
Mr. Wise, so, for this one, isn't it 2 spectators then?
So what will happen?
So it's just neutral?
Exactly. See if I get any comments here. No, they're still working away. That's fine. This, by the way, in some way or other is a really typical multiple choice question on the AP. So if you have this skill, usually there's 1 or maybe even 2 that you'll get right on the multiple choice. Okay, let me pick some people to do these, okay? So I'm just going to say the first one, how about, and you can send your answers to Aaron. And for the answer, you don't have to give me the proof, but how about you give me the acidic, neutral, or basic guess at least? That's easy to type in. So how about the first one, Maria? Can you send an answer to Aaron? For the next one, how about Noah? For the third one, Quinn and how about Sarah for the last one?
Leah saying acidic was, so the first one.
Okay, Ray is saying acidic. We'll fill these in and check and see if we all agree or disagree. I'm glad I picked your favorite, Quinn. Quinn says neutral for that one. Good. Noah says his is acidic. And we'll wait for Sarah to try the last one.
She's saying basic.
And Sarah says basic. Thanks, everybody. That was kind of fun. I hope so. Okay. And thanks, Aaron, for your help in doing all this. All right. Okay. Okay, some spectators. How about Aaron? Can you give me some spectators out of here would be?
The second one?
The first one.
I.
I minus. Next one?
NO3.
Minus.
Then KClO and 4 is all of it is spectator.
It's both, as you asked me about earlier. And the last one.
Na+.
Good. So there's the spectators. Hopefully everybody's got. I'm guessing you have because everybody sounds like they're doing pretty good. Okay, so for the proof of this thing, let's see what's going on. I got NH4 plus water. And let's see what's going on. Acidic. Yeah, because what happens is, well, there's two ways to write this. Actually, I could just say pull off an H and I get H3O plus, which is another name for H plus. You still on there? Yeah, they can still see. Plus, what's left is NH3. Or if you do my cheater way, you can also write it like this. NH4 plus gives off an H plus, and you're left with NH3. Cheryl would prefer you to see it as H3O plus, hydronium. I don't really care, at least for thinking about it. As long as you know there's an H plus, so yes. Thank you, Urea. So, looks good. Looks like we got an acid, all right. Okay, the bell's ringing, but you guys are home, and I agreed with Aaron. We're going to just walk right through and continue until 11:15, and then we're going to stop class right at 11:15. Folks at home, then you can do what you need to, and Aaron can here as well. Okay? Yeah, good. Thanks for your participation. So let's check Noah's here on the next one. So I got NO3 minus is out of there. So zinc should do something. Zn2 plus, throw it in the water. Let it swim around. And sure enough, it's going to grab onto, well, I'll just ask Aaron, it's going to grab onto two what? OH minuses. So I got zinc hydroxide. And so therefore I got two H pluses, or if you like, two hydroniums. Whatever floats your boat, okay? You can say H pluses there or H3O pluses. Whoops, I just lost you. There you are. Okay, am I still rolling? Yeah, okay. Yeah, so it's looking like acidic. So thank you, Noah. Okay, for Quinn saw that both of these suckers are from, in this case, a strong base and a strong acid, and therefore these spectators are the only ones present, just like NaCl would be in water. They don't do anything, so it's neutral, no reaction. They'll just be floating around, interacting with the water, but not really doing anything, not pulling the waters apart. And from Sarah, Sarah's realized I got Na plus here, so the fellow that's going to do something will be PO4 3 minus. And let's drop in some waters. How about 3 of them? And essentially what happens is it becomes a weak acid. So it's going to rip apart some waters and make phosphoric acid, which some of you may drink a fair amount of. That's the one in Coca-Cola. Plus some H pluses or some OH minuses. 3 of those suckers. So 3 of those makes it basic. So thank you, Sarah. Those all look great. Wow, it's really blowing here. Okay, I've got, special effect. Sorry, special effect there. Okay, so. Good, thanks everybody. Hope I made you laugh. Okay, here we go. So again, what you've learned, I hope, is that you understand a powerful tool. Most chemicals that are not some organic thing that you put in water, you guys can figure out what it's going to do to your water. It's going to make it basic, acidic, or whatever, and that's kind of a cool thing. The problem, as you could just about guess, so now you're going to become advanced chemist, if you're not that already. The problem is this, right? What if the cation and anion both affect pH? Well, you don't panic, and it won't be neutral. Here's what you do. Let's take an example to show you kind of what to do. Example, let's let it be NH4F. All right, so here's the deal. You know from up above, that was the one Rhea did, that I've got 2 equations here. I've got NH4 breaking down essentially to H plus NH3 minus. No, NH4 plus, pardon me. NH4 plus breaking down to H plus and NH3. And then the other one, and how about I get some help from Aaron on that one? So Aaron, if I drop a F minus into water, what's going to happen here?
It's going to react with an H to make FH.
Mm-hmm. So let's call it HF.
Oh, HF.
That's all right. And then what's left?
And then
OH minus. So say, okay, so the top one is, if you think about it, what we'd call a Ka, right? It's an acid breaking down into parts. So we're going to look up the Ka value for that, okay? Or OKA in this case. And the magic page was, I think, 567. Let's see if my old senile brain is still working for that. It's 567. Hallelujah, there it is. Okay, so everybody look at page 567. And Quinn, you may have to Google this data if you need it. And so let's find the ammonium Ka value. All right, and I got to look too because I don't have that one memorized. If you find it before I do, let me know there, Aaron.
Yeah, it's 5.6 times 10 to the negative 10. It's towards the bottom.
Thank you, got it. Okay, 5.6 times 10 negative 10. Super. Okay, the other one I think you can tell everybody it's a KB reaction, right? Because it's making a base. So the KB, and I'll go back to page 567. Oh man, they only got KAs. What can I do? Anybody remember from last time we met? If I've got a KA, how can I get the KB? And while you're thinking about it, I'm going to look up the KA for this. Okay, so what you do, assuming the windows don't blow in, is, Aaron?
Oh, you have to multiply the KA and make the, and that would equal to K of water.
Beautiful. Good. I'm going to write that in just a sec. So the only thing I can look up on page 567 is the HFKA. And that is, I just lost my place. No, could you find it for me, Aaron? So the KA here for HF.
3.5 times 10 to the negative 4.
Okay, so to get the KB, we're going to do just what Aaron said. You may not have heard it, but she said, well, the KA times the KB. We learned that up to the KW, like that. So the KA, 3.5 times 10 to the negative 4th times the KB, which we're going to solve for, equals 1.0 times 10 to the negative 14. Let's make it like that. Okay, so you might say, why are we doing this? Well, we need both of these to kind of compare is what we're going to do. Okay, so let's say, I can't do it mentally, but it should be sometimes 10 to the negative 9th or 10th. Aaron, what'd you get? I'll let you do it. That's okay. Everybody at home should do it too. Make sure we get the same thing. 1 times 10 negative 14th divided by 3.5 times 10 negative 4th.
I've got 2.86 times 10 to the negative 11.
And that looks good. You're right. It's going to be 11, not 10, because we multiply the front numbers. Yeah, that looks all right, I think. So let me put that up here, and we're going to kind of compare them. So what you got to do now, everybody, is really put your thinking caps on. You're all good thinkers anyway. And I just lost you. There you are. 2.86 times 10. Good. So Shilpa got the same thing. Thank you, Shilpa, for punching that out. So that looks good. And now we got to ask the question. Ready? Which ion, using these two numbers, has a greater effect? See if you can guess, studio audience, which ion will have a greater effect based on these two numbers. If you can't read them too well, 5.6 times 10 negative 10th and 2.86 times 10 negative 11th. What do you think, Aaron?
I would think it's more acidic.
Mm-hmm. Why?
Because, I mean, the acidic K is the larger number.
Yeah. Good. Let's see if anybody else typed that in for fun. No, not yet. Okay, so Aaron's observed that the Ka is bigger. And if it's a bigger number, it's going to be the more important reaction. Okay? So what that means is if the Ka is bigger than the Kb, she's exactly right. It's going to be an acidic solution. So now I'm going to have you guys do this, okay? And you're going to try a couple of them. It's not easy, all right? And you got to use the data on 567 or For Quinn, you may have to like Google all the numbers or find just a table on the internet, Quinn. You might be able to find that. So here you go. Let's just do 2 of these because these take a little bit of time, okay? So this time I want to make a table, but I can't make it like this, can I? Because it's a different ball of wax. And you know what? Before I have you guys try some, you know what? Let's come up with just a general way to say this, okay? So let's call this predicting with Ka and Kb. So if the Ka, like the one we just did, is bigger than the Kb, then the salt is acidic. And when we say a salt is acidic, that's kind of assuming we're throwing it in water, all right? But that's how people say it in chemistry. It's an acidic salt, just to get you used to that. And you guessed it, Chester. So if the Kb is bigger than the Ka, the salt is basic. Are they ever equal? Pretty unlikely. I haven't ever seen it, and I really wouldn't worry about that case. Because if I haven't seen it after all these years, probably they're not going to throw it to you on the AP. Yeah.
So even if you have like very slight differences in the numbers, you would still just go with whatever it is the bigger one.
That's correct. Yeah. Aaron asked if there's only a slight difference, you still go with the one that's bigger, and the answer is yes. So that's the deal. It may not be a really, really deep blue or a really, really dark red, but it will be enough to show that the solution is clearly acidic or basic. We're going to do a lab on this, and I hope I have more of you here. I better schedule for next week after any storms gone. Well, this is our last day this week anyway. So next week we'll do a lab on salts and have you measure with some pH meters. And I think you'll see that it's not always real intense, the effect. And we'll see during our lab why that is, okay? Reach some kind of cool conclusions in our lab. Okie dokie. Ready? Here we go. Let's have you try 2 of them. So let's go salt, and let's find, let's do it this way. Let's find the Ka number. Let's find the Kb number. And then it'll just be acidic or basic. Yeah, that's kind of what I want you to do. So let me dream one up first off. Ba-da, 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 ba-da. How about, yeah, I want that one. And I want that one. Okay. Okay, so here you go. Your first salt's going to be well, let's make sure you can do that. No, you can't do that. Okay, I better give you something nicer. Hold on. That one you can do. Or can you? No, that's no good. Well, let's do that one for starters. Okay, so we'll do NH4ClO. That's kind of a problem. I know. I'm trying to come up with a good one here. Yeah, we don't have that data, so what am I going to do here? I guess I could do the same thing again. So makes it a little easy, but that's too bad. So let's do that, okay? With CO3. And then I think you got a chance of using it with the data you got. In fact, no, I can't even do CO3. I got to do HCO3. So stop. NH4, HCO3. And you got data for it. Okay, so NH4ClO and NH4HCO3. I guess I don't need parentheses here.
Mr. Weiss, so do I just need the Ka from NH2?
Yeah. So that I think we got already. You got it in the notes. There it is up there. Okay, so I think everybody, we can just write the Ka. So we already looked it up there. So that's the same for both. 5.6 times 10 to the negative 10th. And to get the KBs, don't forget the trick that Aaron described here. Ka times Kb equals a Kw. So you'll have to solve for the Kb in each case.
Would the Ka be the same as H2CO3 for HCO3? Or no? Because I can only find H2CO3. Oh, never mind, I found H2O3.
Yeah, it should be on the other side. Oh, no, there it is. Yeah. Okay, all right. Oh, interesting. Oh, that's going to make it interesting. Okay, so what can I do here? Right. Okay. Okay, so for the KBs,
Sarah asked if we also need the Ka of the other ions. I think she was confused because we're asking for the Kb.
yeah. So here's the deal. ClO minus, if we look for it, it is not on your data table. Damn it. Okay. All right. My old data table, it was on there. Doggone it. Okay. So I got to give you this. All right. Oh, that stinks. Okay. So for ClO minus, sorry, that's what happens when you change books. The Kb is 3.6 times 10 negative 7. And for the other one, we still got to get the Kb. So we're going to do the Kw divided by the Ka. Okay, it's a sensor you can find this data. So for that one, really check it out. For HCO3 minus, it's the hydrogen carbonate ion down towards the bottom of the page. You got the Ka. You don't want that. You want the Kb. So we've got to have that sucker going 1 over that. I believe. Okay, no, I take it back. Take it back. For the HCO3, if you think about it, you've got it. It's on the right side of the reaction with carbonic, so CO2 and H2O. So H2CO3, and on the other side is HCO3 minus. So that's the Ka we want. And we're going to divide that sucker. We're going to divide the Kw by that sucker. So 4.3 times 10 negative 7. Okay, so the top one, let's answer right away, okay? Because I bet you got that one.
Mr. Weiss, where did the 14.3 come from?
I'll show everybody in a sec. Let's do the top one. So from the top one, is it acidic or basic? Top one, acidic or basic? Well, Aaron?
It's basic.
It's basic. So the basic one is bigger. Negative 7 is bigger than negative 10 as a power, so it's basic. Okay, for the bottom one, and I know that's, thank you, and I see Shilpa and Noah agree.
Yeah,
Perfect.
yeah.
So here we go, and Sarah too. Good. So here we go. For the bottom one, I want to make sure you know where to look. So what's going on? The NH4, we know what the reaction is. Here, let's just write it down here. NH4 plus, that can be a potential acid. And I get NH3 on the other side. But look at this sucker. HCO3 minus. It can actually do two things. If I drop it in water. But let's play the game for now that it's going backwards. I should not have picked carbonate. I'm kind of kicking myself. Okay. Let's have it go backwards and go to H2CO3 plus, well, if it grabs an H plus, then I got it as a base. So essentially, everybody, I want you to get the Kb of this. So you got to get the Ka of H2CO3, and I think, everybody check, it's that, 4.3 times 10 negative 7th. Aaron, can you look and see if that's the one you find too for H2CO3? Somewhere in the middle.
Yeah, 4.3 times. Yeah, that's right.
Okay, so I'm taking the Ka, everybody, of H2CO3. But it's going, I want the Kb for that. So I'll divide it 1.0 times 10 negative 14 by that. And so let's see what we get. Aaron, can I have you do that just so everybody sees the number? And we'll see if others get the same thing.
Uh, 2.3 times 10 to the negative 8.
Okay. All right, so there it is, and there's my Ka to negative 10th. So again, this one looks like it's going to be yes, basic. Yeah. Okay, now that's okay, but I really should not have picked. Thank you, Quinn, and Shopa, and Noah, and probably Sarah too. So thanks, everybody. I should not have picked carbonate because carbonate's sort of special. It's amphiprotic, kind of like we talked about the other day. So first off, let me pause and just see if you have questions on how to do this. You're going to do a lot more as you go through the book eventually with Sherry. She has you do a lot of checking this Ka, Kb business, so it'll become pretty common for you. But I hope you get the idea. And if you get confused, really write reactions because that's what helps me. If you're unsure, write it so you have an idea. Aaron.
I'm just kind of confused why we use the value for H2CO3 when we use the value for NH4 plus and the other one.
Yeah.
Like the Ka value.
Okay. When I look at the two, Aaron's question is how do I know what to choose which values? Here's how I know. If it's NH4 plus, the good thing about that chemical, folks, is it can only do one thing. It can only lose an H plus. Like I can't attach another H plus on there, if you know what I mean, because it's already positive. So that sucker's going to act like an acid. So I definitely need the Ka for that. Well, if that's the case, then the other one better be acting like a base. And that's why I know I've got to have the HCO3, when it contacts a water, grab an H plus and act like a base. I've got to have it do the opposite, so to speak, Aaron. So I know I got to look up the Kb. And help, if I write this reaction, then I know what to look up, okay? Well, the Kb, but how do I find it? Well, you find the Ka for the what's called the conjugate acid, right? Remember that word conjugate, the connected acid. So I knew I had to look up H2CO3 to find that value. And that's the Ka that we divided the Kw by that to get my Kb. Okay, does that help?
Yeah.
All right, good. Other questions from folks at home? I know it takes a while to type them in, but if you have something or don't understand something, please type in, because I know this is pretty AP. This is pretty complex. Okay, while you guys are thinking, I'm going to make a little board space over here. Stay.
Would we get this list of Kas for the AP?
Good question. Would you get this with the Kas, Kbs? Well, would you get it with the Kas on the AP? Yes. You might get it with the Kas, but they would expect you to get the Kbs then from that. Yeah. Or AKB. But they'll give you the data. You won't have a table. You'll be able to just see it in the problem on the AP Chem test and on the clausura as well. Okay, so what do? Or what about amphiprotic species? What do they do to pH? Or maybe I should say more scientifically, how do they affect pH? Let's find out. Okay. Let's take that pesky old carbonate. So I want to look at HCO3 again. And this time, or it's called the bicarbonate ion, if you remember. Bicarbonate. That's one you guys memorized long ago. I'm sure you can see that. So we're going to play with the bicarbonate ion here. It can do two things. Remember, amphiprotic, just like amphibians, they can live in water, they can live in land. Well, this guy can act like an acid or a base. So add some water, add some water. So we're going to let the amphiprotic fella swim around twice. Let's let it first grab an H plus off the water. So now I'm going to get H2CO3 plus OH minus. Oh, that should look familiar. That's what we did in the last problem. That's salt. But sometimes it can do the opposite. In other words, what if I pull off an H plus from the CO3 minus, then I get CO3 2 minus, and now I get on the other side H3O plus. Okay, so the top one, it's acting like a base, right? The bottom one, it's acting like a acid. Holy smokes. So what do? Well, you got to do some comparing. Okay, so I'm going to give you the data already. Let's say the top one, let's make sure I said it correctly. Yeah, that's acting like a base there. Okay, the top one, I'll give you the KB for it. And I think it's what we had in the last problem anyway. So it was 2.3 times 10 to the negative 8th. Yeah, we had that before anyway. And then the Ka is the other number we stuck in there. No, it was not. The Ka is, according to this data, I've got 4.7 times 10 to the negative 11. Okay, so in spite of the fact that bicarbonate can do both things, it can either act like a base and set free some OH minuses, or it could act like an acid and form some hydronium ions, which are more or less H pluses. So it can act like a base, therefore I've got a Kb number. It can act like an acid, therefore I've got a Ka number. The nice part is, you ready? You still do the same trick. Which is bigger? It'll have more of an effect being a what? So in other words, if I throw it in water, what will it do more of? Hen or hen? So why don't everybody type in? Type in KB or Ka, which will have more of an effect. Okay, good. Thank you, Noah. All right. Thank you, Shilpa. Good. And Aaron, it's going to be, you got it. So what that means is it's a basic solution.
Yeah, Rhea also said KB.
Thank you for relaying that. Thanks, everybody, for typing into Aaron, too. Ray and Sarah. So it's basic because the KB is bigger than the KA. That's the Scoops key. Now, I know it's gotten weird, but it turns out this is something kind of cool, okay? So here's something practical after all of that. I don't usually buy this because I don't have an upset stomach, but if some of you buy products because you get an upset stomach, then in the US, I know what they were called. They were called like Tums and Pepto-Bismol and blah, blah, blah. I don't know what they're called here in Germany, but a lot of them are called antacids. So antacids are products to settle your stomach. By, well, like its name suggests, right? Antacid, anti, right? By absorbing, so to speak, stomach acid. And one of the most common ingredients in these antacids is, including, if you've been in America, Tums, or Rolaids is another one. Many contain sodium bicarbonate. And now you know why. So again, think it through. The sodium, of course, does nothing, but the bicarbonate, we've proved that its KB is bigger, so it acts like a base. So it essentially creates OH minus. The OH minuses react with the acid, the H pluses from your stomach acid. Remember, you have HCl in your stomach, and neutralize it, don't it? So you get to neutralize your stomach acid. For that effect. Yeah.
Is there a reason that they use an antiprotic ion rather than like a strong base?
Okay, it's a really good question. So Aaron's question, and I'll get to Quinn's pun in a second here. Aaron's question is a good one. She says, why don't they just use a strong base? Well, it turns out you could use a strong base, but it ends up being too strong. And it's pretty hard for your body to deal with a strong base. It can do damage going down because your esophagus and all of this is not, it shouldn't be exposed to any sort of strong base either. And yeah, strong base is just too hard on your body. But a weak base, like this one, is enough to sap up the acid in your stomach. And even if there's a little extra, it's not going to be a big problem in your stomach. If there was some extra strong base, you'd have a problem in your stomach, okay? So better a weak base like this one that's in many antacids to do that. Okay, now I get to play doctor about the only time of the year, okay? And it goes like this. If you have an upset stomach, what you can also do is use baking soda. On the rare occasions when I have a stomach problem, I take a little baking soda, not much. So baking soda, if I take 1/4 of a teaspoon, that's not much, in a cup of water. And guess what? Baking soda has in it sodium bicarbonate. Ha! It's what makes your cookies rise or your rolls or whatever rise, okay? So if I do that, it tastes terrible, by the way. But really quickly, you'll feel better if you've got kind of what my mother used to call a sour stomach, if you've got a lot of acid in your stomach. And sometimes they have this actually on the container of baking soda as another use you can use it. It has a lot of uses, actually, baking soda, in addition to baking. So there's my household hint for the day. Let me go back and read your comments. Yeah, exactly, Quint. I like it. So I could use an ant acid against ant bites. Theoretically, I could grind a little into the ant bite because ant bites have formic acid or ant acid. In German, Ameisensäure. I love it. So yeah, that's kind of fun. Thank you, Quint. I guess, Quinn, taste vary. I find it tastes pretty bad, but I always feel better afterwards. And Shopa asks, couldn't you just eat some basic foods to neutralize your stomach acid? Maybe, Shopa. The problem is we don't eat a lot of basic stuff, human beings. So I'd have to think about, other than baking soda, I'd have to think about what stuff we eat that would actually help your stomach. Most of the stuff we eat has some acid in it, and you'll find that out when you do the Sherry chapter 5 and 6. She has some consumer products she lists, and I have you check out a few of them. And sure enough, most of them are acidic. We just don't eat a lot of bases. So yeah, kind of hard to get to first base that way. Pun intended. Bad pun. Okay. All right. Other questions, comments so far? Ute. Okay, so maybe I better jump ahead because we're going to need to know this. We got any time left? We got about 1 minute left. So I'll just allude to this. We're going to talk also at some point about diprotic acids. Let me at least tell you what a diprotic acid is. So diprotic acids, just for the future, have 2 protons. Wow, big surprise. Like H2CO3, like H2SO3, like H2SO4. You know what I'm saying? So we'll have to treat those in a special way too. But a lot of them are kind of like what we were doing with the H2CO3 system, okay? And we'll see how to do that probably another time when I see you, okay? Thanks, everybody, for joining in. I'll save this so it'll be in our class stream on Google Classroom in case you want to refer to it, and for those that couldn't make it to the live stream today. Thanks, Erin, for being here. Everybody owes Erin a cookie because she really did a good job of coordinating communication. Have a good day. Stay away from trees. Bye-bye. Well, I am really trying to end this thing. Here we go.